Welcome to the presentation on pattern matching algorithms. In this video, we will explore the concept of string matching using finite automata. We will delve into how finite automata can be used to efficiently find patterns within larger texts. So, what exactly is pattern matching? At its core, it's the process of finding occurrences of a specific pattern, which is essentially a substring, within a larger text or string. For example, consider the text ABABCABABA, and we want to find the pattern ABA. By using pattern matching, we can identify that ABA occurs at positions 0, 5, and 7 within the text. One powerful approach to pattern matching involves using finite automata. The core idea here is to construct a finite automaton, which is a type of machine that recognizes the pattern we're searching for. This automaton then processes the text character by character. The process involves 4 key steps. First, we construct the automaton specifically designed for our pattern. Then we scan the text from left to right, feeding each character into the automaton. As we scan the text, we keep track of the current state of the automaton. Finally, when the automaton reaches its final state, it indicates that we've successfully found an occurrence of our pattern in the text. Now let's discuss how to build the automaton. For a pattern of length m, we create m plus 1 states. Each state, I in the automaton, represents having matched I characters of the pattern. The transition function, denoted as delta of q, and a, is defined as sigma of pq plus a. Here, sigma of x represents the length of the longest suffix of x, that is also a prefix of the pattern p. Let's consider an example where we want to construct the automaton for the pattern ABA. First, based on the length of the pattern, we create 4 states, namely Q, Q, Q2, and Q3. The state transitions are as follows. From Q, upon encountering a, we move to Q. From Q, upon encountering B, we transition to Q2, and from Q2, upon encountering a, we reach Q3. Hence, the final state, Q3, indicates that we have found the pattern ABA. Here's an example implementation of the finite automata search algorithm in Python. The function finite_automata_search takes the text and pattern as input. It initializes the state to 0 and an empty list called matches. It then iterates through the text, updating the state using the transition function. If the state equals the length of the pattern, it means a match is found, and its starting index is appended to the matches list. Finally, the function returns the list of matches. The pre-processing step has a time complexity of big O of m, cubed times the size of the alphabet, while the searching step has a time complexity of big O of n. The advantages of using finite automata for pattern matching are numerous. It offers linear time scanning with a time complexity of big O of n. Its behavior is deterministic, ensuring consistent and predictable results. It doesn't require backtracking, making it efficient for large texts. It also provides a solid theoretical foundation for more advanced algorithms. Due to these advantages, finite automata find applications in various fields, including text editors and integrated development environments or IDEs, DNA sequence analysis, network intrusion detection, and compiler design. In summary, finite automata offer an elegant solution for pattern matching. They provide linear time text scanning after the initial preprocessing stage. These automata serve as a foundation for more advanced algorithms like the Knuth-Morris-Pratt, or KMP algorithm. They also have wide-ranging applications in computer science. This concludes our discussion on pattern matching using finite automata. Pattern matching complete. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.